Well, students, let us continue the part 2 of the lecture 6. Here we will discuss more about solution and compounds, because they are the main phases present in any phase diagram, because I cannot discuss every part of the phase diagram as a part of this course, which is the one subject itself. So, we are talking about only bits and pieces or important aspects. So, what I told you is the solutions can be two types, substitution solution or interstitial solutions, right. So, interstitial solution means the one of the atom is smaller compared to the other atom. So, why it did not go? Let us look at it. Let us talk about a BCC structure. This is a body centered cubic structure, right. You can see here the center atom at the body center. Now, if you look at carefully, I can have a octahedral void here. How do you know it is octahedral void? Very simple. You can see you can form an octahedron. They are the two unit cells. That is another unit cell here, correct, which you can draw. Okay, I have not drawn it. So, this atom is part of that unit cell in the body center position, correct, and this atom is obviously body center position of the unit cell at the below. And now, these two atoms are sitting at the corner of the octahedron. So, octahedron is basically 8 phase solid. We can easily draw the octahedron. I can draw it easily for you. So, I have a point here, I have a point here, I simply connect it. Okay. So, this is one octahedron. What I am doing? I am connecting this points with the central point. Similarly, I connect although it is not good, but still it is octahedron, and this is the octahedron. You can see I will show by outlining this octahedron in a nice manner. This is the base of the octahedron, and these are the points, these are the connection. So, there are 6 faces of the octahedron. Octahedron has 6 corners, but it has 8 faces, right, because there are 4 at the top, 4 at the bottom. That is why it is called octahedron. And this atom, small atom, is sitting at the center of the octahedron, that is called octahedral voids. So, everywhere there is octahedral void, every face actually, because you can see how it can form. Already one is present, so there is another atom, you can easily form the octahedral voids. Am I clear? This is for BCC structure. There are many such octahedral voids, you can figure it out. Then you have FCC structure. Very easy to form octahedral void at FCC structure by this way. So, you can see here, I will draw it here for your purpose. So, if I draw these 4 atoms first, I draw 4 atoms, right. So, this is what is connected by that. Now, I connect this like that. This is one, then this is another one. So, this is an octahedron, and in the center of the octahedron there is an atom. So, let us draw a smaller atom, because this is a void, this cannot have bigger atom, that is what it is. So, that is one of the octahedron. There are many octahedron possible in this FCC structure also. So, this is a void, that is why in the voids, octahedral voids, atoms can easily go and sit. You can also have tetrahedral voids, which I have shown you for the diamond cubic structure. Please go back to my lecture number 4, you can see diamond cubic structures. Now, these are the solutions. You have substitution solutions, or you have what is that called, the interstitial solution. There are 2 types of solutions present in these kind of systems, and both I have shown you. So, carbon in iron form, from the interstitial solutions, because carbon goes to interstitial positions. Interstitials means the locations where there is a free space available, like octahedral void or tetrahedral voids. On the other, nickel in copper form a substitution solution. Similarly, if you add nickel in iron, it will also initially form a substitution solution, small quantity of nickel. For copper and nickel, any amount can form solutions, there is no problem, but for every system it is not the same system. Like here, it is a nickel iron, nickel aluminum phase diagram. This is a very classic phase diagram, because this is what is used for superalloys. We will talk about it later today, or maybe otherwise lecture number 7. So, you can clearly see on the left side you have a nickel, 100% nickel, right, and you have right side you have 100% aluminum. Here it is atom percent, it can be weight percent also, does not matter. So, this is what you can add aluminum into nickel, still form a solution, and solutions are marked by this. So, when you see a bracket, small first bracket around a metal atom, it is called a solution. But other than that, on the right side you have also aluminum solution, but very minute quantity of nickel can go into aluminum. On the other hand, large quantity of aluminum can go inside a nickel. So, there is reasons for it, let us not talk about it. Other than that, whole phase diagram is consisting of compounds Ni3Al, NiAl, right. You can see Ni3Al, NiAl and what not, Ni5Al3, Ni2Al3, NiAl3. So, these 5 different compounds are present. So, they are also part of the phase, right. So, what are they? So, I talk about one particular aspects, that is Ni3Al, others also can build up. So, Ni3Al is very important PCs or microstructural as species for superalloys. Superalloys are used in the turbine engines which run the planes actually. So, what actually happen is very simple. If you have a solutions of copper, say aluminum and nickel, then this is what will be. You can see here, this is a face centered cubic structure. How do you do face centered cubic? There are 6 atoms in the face centers and there are corner atoms in the unit cell. So, they have same color. So, they can be either aluminum or nickel obviously, because you do not know which one is what when it is a random solution. So, when you add aluminum into nickel, this is what will happen. Some atoms of nickel will be replaced by aluminum. So, now for Ni3Al, it is not the case. Ni3Al has 3 nickel atoms and 1 aluminum atom in the unit cell. So, we will do that how it happens. So, you see there are 6 faces occupied by 6 nickel atoms and 8 corners are occupied by aluminum atoms. So, 6 faces is occupied by 6 nickel atoms means what? 1 by 2 into 6. So, nickel atom is how many? 1 by 2 into 6 is 3 and aluminum atom is how many? 1 by 8 into 8, I already talked about it. So, that is why it is 1, that is why it is 3. So, 3 atoms of nickel and 1 atom of copper. This is a compound and you can clearly see this is not a fixed stoichiometric compound, it has a small window where aluminum concentration can be changed, but still it will have similar structure. Same thing is valid for Ni2Al3, but on the other hand Ni5Al3, NiAl3 are having fixed stoichiometric compounds. There is a line, you can see there is a line, it hits this x axis which is the compositional axis, that is what aluminum atom percent is written. This is also hitting a particular point, there is a line. So, they are having fixed stoichiometry unlike Ni3Al or NiAl. NiAl has a large, very large window of composition variation possible. NiAl is also very high melting temperature, it is almost close to 1600 degrees Celsius temperature, melting temperature, much higher than both aluminum and nickel. Correct. That is what is very interesting part of it. So, NiAl is a very strong high melting point species. It can be used for various purposes, but compared to NiAl, NiAl has a BCC structure. Okay, let me draw it for your purpose if you want, because this is something you should know very well. So, NiAl has a body centered cubic structure. I will draw 2 unit cell of NiAl to show you one where every atom is a random. So, corner atoms as well as body centered cubic, right. That is what is Al or Ni. On the other hand, if I have specificity like this unit cell here, then it will be different. Remember, each unit cell has 1 atom of aluminum, 1 atom of nickel, that is why it is called NiAl, right. Otherwise, why it will call NiAl? The chemistry is 1 atom nickel, 1 atom of aluminum. So, you have let us put aluminum atom here. I think better we put different color, otherwise this will not look good. This will be confusing for you if you want to look at later for prepare of exam or something. So, for aluminum let us use same color, this. So, corner atoms are aluminum and you can see 8 atoms. So, 1 by 8 is 1 atom aluminum, nickel, and this is your aluminum. So, this is called B2 structure, this is called a BCC structure, because it is locations of the unit cell, corner and the body center occupied by different type of atoms, that is why, but here it is average. Okay. I have not put that atom here, that is why probably you are thinking here at the body center there is one atom, you can clearly see there is a body center, there is an atom there. So, that is what is the difference between NiL and Ni3L structure. They are compounds, okay. They are not solutions, and these compounds have some range of compositional adjustment possible, but some other compound it is not possible, like Ni5Al3 or NiL3 is not possible, okay. Then structure will change. So, this classic phase diagram, which is used for various kinds of applications, are actually important for the humanity. Why? Because jet engines, all of you know that you fly in planes, they have engines, and engines actually are called jet engines. What is jet engine? Jet engine have this kind of blades, you can see here, this is one such blade shown here. These blades are mounted on a rotor and rotates at very high speed by using of burning of fuel, that is what gives you the power, and these blades are actually made of Ni3Al composition. Okay, especially superalloy composition is based on Ni3Al. There are many other elements present. There are 13 elements present in this kind of alloys, and that is basically one of the major discoveries of material science, which has given the best technology possible in this world. This blades are actually single crystals, by the way, they are single grain, each blade is one grain and they can be 1 meter long. So, each blade, this blade you can see here, this can be 1 meter long and the whole is one grain, there is no boundary in this, just like grain boundaries you saw, and they look like this, you can see here they are little bit bent and they rotate at a high speed, something around 50,000 to 60,000 rpm, very high speed they rotate. That is what gives the very large power to the moving planes, and these are the made up of Ni3L chemistry. So, let me just explain a little bit about steel again, because this was part of the explanation for solution versus compound, right. But in the process we brought about nickel aluminum phase diagram, copper nickel phase diagram. So, plain carbon steel actually has very low carbon steels like 0.3 to 0.4% carbon, medium carbon is about 0.3 to 0.8, high carbon 0.8 to 1% carbon, and it will also consist small amount of other elements like 0.4% manganese, sulfur. As the carbon content increases, material become harder, but it will also have lesser ductility. That is one of the major problem of steels. Alloy steels, I talked about it, other than iron and carbon, it can contain other alloying elements like moly, tungsten, chromium, nickel, silicon, some of them has aluminum also, a large amount of manganese, more than or sometimes 5% or 10% manganese can be there also in alloy steels. And these elements are added to impart various properties. The best example alloy steel is what? Stainless steel, right? Stainless steel is the best example of alloy steel. Stainless steel contains chromium and nickel other than iron and small amount of carbon. So, its chromium and nickel concentration can vary actually. It is actually large amount of chromium nickel is present. The normal stainless steel, which is we always talk about 304, it contains about 18% chromium and 8% nickel, very large concentration of chromium nickel present in these steels, and that gives you the best corrosion resistance properties. Remember, stainless steel is a wonderful material because this is what is used to process different kinds of corrosive materials, whether it is chemical industries or even metallurgical industries. They use stainless steel as a means to contain things, use as a container. So, therefore, alloy elements can be added for various purposes, not only to give strength, ductility, toughness, but also many other chemical and physical properties can be imparted, like one of these is corrosion resistance. Cast iron, I talked about it earlier, it is basically a product of pig iron in blast furnace. It contains lot of carbon, about 3 to 4%, but specifically about 3.5 to about 4.5% carbon. It also contains quite a bit of silicon, 1, 2 or 3% silicon and manganese, and it can be directly cast from the liquid. That is why it is called a cast iron. It is a good in compression, but bad in tension. It is brittle, but it has a huge amount of vibration resistance because of the presence of graphite as a carbon. Carbon is present as a graphite, not as a carbide here. In steels, carbon is present as a carbide. It reacts with iron, but here because of silicon, it does not react with carbon, whether it forms a carbon flex or round separate carbon. There are different kinds of cast iron present in the world. It has a good corrosion resistance and vibration and damping capacity. I told you more than 100 times better than steels and 2000 times better than iron. It has a good fatigue resistance, and it has also is very good to machine, very easy. The most important use is engine blocks in the cars, or you can use it for machining frames. Many of the frame structures are made of cast iron actually, whether it is a frame for the machines or for the other things, is basically used by cast iron because it has a very good resistance to vibration and high damping capacity. And what alloy element does, like Mn actually improves the strength and the hardness. Chromium improves corrosion, I already talked about it. Also gives you strength, wear resistance and hot hardness. Nickel improves strength and toughness both. Moly increases tensile and keep resistance, keep strength at the high temperature. So why we are talking about these things? See, remember these aspects actually come from experiments, okay, not by machine learning or AI, but this will be our input if you want to develop AI based model. You should have this understanding of the subject, that if I add Mn, it gives you high strength and hardness. If I use chromium, it gives you good corrosion resistance, wear resistance, hot hardness. If I use nickel in steel, it gives you strength and toughness both. Moly gives you high temperature strength or properties. So these aspects is very important for you to understand, because otherwise when you want to model it, if you have no basic point, how do you do it? So that is why experiments have been done extensively on this kind of system like steels or cast irons, which can be widely used. So one of the major class I told you is stainless steel. It is a large family of steels. It contains minimum about 11.8% of chromium, and it can contain even 20% of chromium also. But corrosion resistance is basically due to formation of chromium oxide. Most stainless steels show good short time strength up to 1100 C compared to plain carbon steel, but they lose a strength above 500 degrees Celsius temperature. Carbon conductivity of stainless steels are not good. That is why many times copper cladding is used in stainless steels, cooking stainless steel. You see in the cooking stainless steel plots, you will see at the bottom of the pot there is a copper, because thermal conductivity of stainless steel is poor. So that is why one is to use a copper to transfer the heat from the flame to the food. On the other hand, stainless steel is other side of the container, that gives you good corrosion resistance, other properties. Steel is a wonderful material, whether you like it or do not like it, it is present everywhere, you cannot remove it. Another important value steel is tool steel, which is used for all kinds of tools like cutting tools, many other tools, and this contains elements like manganese, high amount of chromium, tungsten, vanadium. Okay, it is not Va, it is V steel basically, V, moly, cobalt, and there are this gives you very high shock and wear resistance, it withstand high temperature. Okay, that is tool steel are supposed to withstand high temperature because they are going to use for tooling purposes, that is why. And then there are steels which use for electric and magnetic applications like electric steels, is used in transformer cores. They contain silicon, and silicon increases the electrical conductivity and permeability. They are used basically electric motors, generators, transformers. They basically reduces power loss associated with the heating problems. As you know, transformer are actually used to step up the voltage or step down the voltage, right. So when you have get power at 11,000 volts from the power plant, it has to be stepped down to 220 volts, right. That is why the test transformers use, and transformer uses a magnetic core. The magnetic core actually is made up of silicon containing steels, very widely used material. So next 5 minutes or so we will talk little bit about non-ferrous metals and alloys. This was ferrous actually. Non-ferrous are also widely used. Other than iron, everything else clubbed together is non-ferrous. So predominantly used in aerospace industry is what? Aluminum, right? Aluminum actually is widely used in aerospace industry. It's a light. Density of aluminum is how much? Aluminum density is about 2.72 gram per cc. You should know that. Aluminum. Magnesium has 1.71 gram per cc. But if you look at compared to that, We will talk about two metals, one is titanium, other is iron. Iron has a density of 7.8 gram per cc. Cc means cubic centimeter. Titanium has density of close to 4.5 gram per cc. Am I clear? So, you can clearly see from compared to iron, aluminum is much more lighter, almost 3 times lighter, or rather iron is 3 times heavier than aluminum. That is why aluminum is widely used in the aerospace industry, and it can be used either in pure form. I do not think it is used in pure form, that is not correct, it is used in alloy form, which we will talk about it. But aluminum has emerged as a valuable source for metal for automobile industry also. Various car manufacturers, they use aluminum foam or many other aluminum alloys in the car. So, first important alloying things which we will discuss now is basically duralumin. It is almost more than 100 years ago this was discovered. To be specific, 1911 this was discovered, and this is basically alloy of aluminum and copper. Very little amount of copper, about 4.5 weight percentage copper in aluminum is used for duralumin. And what it does is very interesting. It forms precipitates. You can see here in the microstructure. I hope you will learn how to read microstructures now. You see here, these are the black dots of precipitates. This is a boundary here. You can see this, the boundary lines, and this are precipitates. This precipitates actually gives you a lot of strength. So, whole body of the plane actually made up of these duralumin. So, when you fly in aeroplane, you will see it. The plane is basically made of duralumin, and this is one of the major discoveries. So, if you have very less amount of copper, it forms this precipitate alpha plus theta. Alpha is basically aluminum, this is aluminum, solution of aluminum, copper is there little bit, and theta is basically Cu Al2 or Al2Cu, but it is not the only the Al2Cu, there are many other variants of that which actually forms as precipitates, and this gives you very good properties. That is why it is low dense and it gives you very good strength. That is why it is used. It is stable at very low temperature. When the plane goes to the sky, temperature is minus 60 degrees, and when it lands on the earth surface, temperature go down to 50 degree plus. So, minus 60 degrees to plus 50 degrees, this temperature range, these alloys can give you all kinds of properties. That is why it is another wonderful material in the history. Second one is titanium. Titanium is also has a densities between compared to steel and iron aluminum. I showed you it is strong, lightweight, and it is extremely high corrosion resistance. It can be used in the sea water also, but it is chemically very active in molten state. It can absorb oxygen and nitrogen easily from the air, and that can ruin its capacity. It is costly and it is difficult to produce. It forms hexagonal cubic Cospack structure. That is why it is not easy to form aluminum from FCC structure. So, we will talk about titanium alloys everything in the next lecture, but just to show you one application, the nickel titanium is important alloy which gives you shape memory properties. Many of these antennas, space antennas actually uses the concept of shape memory. You can actually take this alloy, make the antenna, and then deform the antenna and to compress it, and then what happen, you take this compressed piece to the sky, heat it up, it will get its own shape. That is what is shown here. This is a neutral wire, you can see here, it is deformed, bent, and after that if you put in cold water, nothing happen, but if you put in hot water, it get back its shape. That is what is called shape memory alloy. It can remain, it can actually remember its earlier shape. So, you give the shape, then deform it to a small piece, and then take it wherever you want, heat it up, you will get back to the shape which you have given earlier. That is why it is called shape memory alloy. This is widely used, it can be used in surgery also, and therefore, what all applications I am talking about, it are real life applications, and that is what should energize you, that how materials are widely used in various applications, and this is the connection which is much better than only looking at scientifically how things can happen. So, with this let us stop this lecture, and I hope you are following it closely. Please read books, because lectures are not enough for you to understand the subject, and when you will do modeling using machine learning, you will see this understanding will be required directly. That is why I am talking about you in this course itself. So, thank you.